dear. Welcome to IMS Gate Academy. I hope you are all good. My dear, with the continue of this series of PYQ, today we will discuss the year of 2021. Okay, so in this year, questions will little bit easier questions. The questions which is previously we have to discuss for the year of 2023, 2022. In this year, the question is little bit easier. Okay, so but where we have to also during this session we have to also discuss that what is the motivation and to ask such type of question, and if upcoming GATE examination, if there is a same concept the question will ask, so how to tackle for the different question of a same concept, we also will discuss about that. Okay, so what is that, Vita? The first question is that a cylindrical of water density 1000 impinges at the center of the flat plate, circular plate, and the separated radially towards as shown in figure. What is that, Vita? So this is your plates, circular plate is there, and you are ensuing a jet, ensuing a water from the nozzle of a diameter, the water jet diameter, that means the nozzle diameter, the water which is ensuing from the nozzle in the form of jet, and that jet diameter is D, and it will directly perpendicular exerts on the plate, and then after that it will glide along the plate in the radial direction. So this is the normal direction and this is your radial direction of the plate. Now, and then there is a spring is there. So while the jet will strike normally on the plate tries to move downward, and ultimately the spring will compress. If the spring will compress, spring are able to develop a force in a perpendicular outward direction. That means perpendicular to the plate, but it is opposite to the in-swing jet. Okay, so this is the questions related to the dynamics, fluid dynamics. That means impact of jet. This question is related to the impact of jet. Okay. Now, what is that? So the plate is resisting on a linear spring. So this is your linear spring with a spring constant. It is given the incoming jet diameter. It is given. If the spring shows a steady deflection, that means while striking the plate, the jet on the plate, the spring will deflect. So this is your static deflection delta. It is also given. Okay. Now, upon impingement of the jet, then the velocity of the incoming jet is. That means what is the velocity which is striking on the plate? So we have to analyze as a control volume analysis. What is that? If the fluid is coming, so we have to take a fluid as a control volume analysis. So this is precisely conservation of momentum principle. So we have to discuss about we have to solve this problem in the form of conservation of momentum. So number first, beta, first identify the category of problem. The problem is categorized in the fluid dynamics, and that in the dynamics we have to study the two conservation of momentum also. That means Euler's equation. We also study in kinematics. So kinematics conservation of momentum and dynamic conservation of energy. So this is the precisely impact of jet, that means force, and we have to use the conservation of momentum principle according to taking the control volume analysis. What is that? So we have to try to solve this one. So there is a spring is that there is this is your fixed surface, and there is a plate is that on that plate the jet will strike of a diameter D, so this plate, and after that it will be move in this direction, a radial direction. It will move in a radial direction. Okay, it will move in a radial direction, okay? It will glide in a radial direction. At a lower portion, there is a spring. That is the model of this question, okay? Now, so the spring will strike at the this is 90 degree, so normal, okay? So there must be a motion of the plate in this direction. Due to the motion, there is a deflection, static deflection. X is the static deflection. This is your static deflection. Okay, no problem at all. So we have to set a coordinate. This is your y direction and this is your x direction. Okay, this is your coordinate. Oh, applying conservation of linear momentum. Applying conservation of momentum, COM. Okay, what is that? And the conservation of momentum, it is a force equation. What is that, beta? This is a force equation. Force equation. And that means it's have a direction. It's have direction. It's have a direction. So this conservation of momentum along y direction. Okay, opposite y direction, downward direction. Okay, so what is that? F in a y direction is equal to mass into dv by dt. You know that mass into acceleration. So if we take m by dt limit sense, so this is a mass flow rate of a jet is equal to change in volume in y direction, delta y direction. Okay, so what is delta mass of jet in? So this is what mass into velocity, mass into change in velocity. Okay, mass into change in velocity. So mass in m1 in velocity at inlet minus mass flow rate at exit, velocity at mass flow rate at exit, velocity at exit. But mind it, this is also in y direction, this is also in y direction. Why? Because we have to use the force, it is in y direction. Okay, so these are the format of this question. Now beta, this is the velocity which is in and this is the velocity which is exit. So this exit velocity in y direction, inlet velocity in y direction, why we have to apply the conservation of momentum in a y direction. So my dear, at exit condition, is there any y direction velocity? No. Why? Because in a y direction velocity, it will turn into the x direction velocity. So this velocity, it is x direction. So inlet, so this is in and this is exit. So exit is not in y direction, exit in x direction. So intuitionally, we have to take a neglect. This velocity is 0. Why? No exit velocity in y direction. No exit velocity in y direction. So this is 0. So what is the ultimately? Force in y direction is equal to mass flow rate at inlet, velocity at inlet in y direction. Now my dear, what is the mass flow rate? Density is equal to mass by volume. If you take a rate basis, mass flow rate, density, area into, this is your velocity. This is mass flow rate, density, area into velocity. Density, you have area, that means the diameter of the jet, it is given. So you have an area. What is the area? Pi by 4 d square. So this is the area and velocity. This is the velocity at inlet. So you have all this thing. So there is m dot inlet into rho a into velocity at inlet in y direction into v1y. This is as it is. Okay. So what is the ultimate? If y is equal to m dot 1 inlet rho, no, not m dot you have to remove it. So this is your rho area of jet into v inlet in y direction whole square. So this is your force in a y direction. Now my dear, if this force is applied by the jet on the plate in a y direction. So this is the force applied by the jet on the plate in y direction. Okay. So in a y direction, if the force is applied by the jet, so spring will try to compress. So spring will apply the same force. Why? Because this is we have to balance the static balance. That means static equation. That means balance the equation, net force. So this force F is nothing. It is a spring force. So in this direction, there is a F spring. And this is the linear spring. So this is your K spring constant into X. So instead of Fy, we have to put K into X. Okay. So here K into X is equal to rho area of Z incoming velocity in y direction whole square. Put all this value. K you have 1000. Static deflection you have 0.01. Density you have 10 to the power 3. Cross section area you have pi by 4. Diameter you have 0.01 square. Velocity incoming velocity you have to find it. So if you find it, velocity in y direction, this is your 11.28 meter per second. This is required answer. This is a very simple question. This is your very simple question. So I hope you are enjoying this question with this detailed analysis. So what is the velocity? Velocity is your 18.28 meter per second. Clear? So this is question related to fluid dynamics and the category impact of jet. How to solve this one? This is solved by conservation of momentum. That's it. So these are the model of this question. Now we have to take the next problem. What is the next problem? This is the next problem. So this is also a good question. Why? It is also very simple question, but why it is a good question? This question gives us some insight. What is that? Consider a fully developed, steady state, incompressible. So this is the read this line. These are the not a beautification of this line. This line have a real meaning. What is the meaning is that? See, consider fully developed. What is the fully developed? Number first, steady state. What is the steady state? Number second. Incompressible. What is the incompressible? Number third. Number fourth, laminar. So this is laminar. Number 4. Number 5, viscous fluid. Number 5. So 5 term it is given. What is that? Fully developed, steady flow, incompressible fluid, laminar flow, viscous fluid. So these have a meaning. What is that? We'll discuss. Between the two large, what is the mean by the large here? Between the two large, parallel horizontal plate. So there is a flow between the enclosed surface. Flow of the fluid between the enclosed surface. The enclosed have a different geometry. Either in a circular, flow inside the circular tube, flow inside the duct, rectangular duct, flow within the two plates, like that. There is a internal flow condition. So large parallel horizontal plate. What is the large parallel? What is the meaning of? First we have to design the model of that problem. What is the model? Is that one plate is there, other plate is there. What is the large is there? Large, that means the plate which is perpendicular to the board. That means perpendicular to the flow direction is very large width. That means a large plate, that means width of the plate is large. And the fluid is flowing in between that one. That means fluid is flowing along the length of the plate. So length of the plate is a much less than, hello sir, much less than, length of the plate is much less than as compared to width of the plate. So what is mean by that? That means fluid is flowing in a one direction, single direction. So you may think like that, okay, sir, if this is a plate and another plate is there, so fluid is there, so the fluid may be flow in the lateral direction also, but you don't think like that. Why? Because the plate is large. That means the width of the plate, that means the dimension which is perpendicular to the flow direction is very large and compared to the length of the plate. So what is the time? Is time taken by the fluid from inlet to outlet along the length of the fluid is very less time inlet to exit fluid as compared to exit in the width direction, that means perpendicular to the plate direction. So we have to consider only the flow around the length of the plate, so that the flow is a one dimensional. This is very important. If there is a penetration on the plate is there, so there may be a y direction. But if there is a large plate is there, my dear, large plate is there, that means there is any flow perpendicular to the plate. That is very important thing. So if there are large parallel plate, that means a large it is given, that means it is either two dimension or a one dimension. But if you consider, why? Because that is called the planar flow. That is called the planar flow. Planar flow, it is one direction or it is in two direction also. So if there is a plate without the penetration on the plate, there is any vertical motion of the plate. So vertical motion is zero. Now there is we cannot consider the fluid is move in the lateral direction, that means perpendicular to the plate. So second direction also negligible. Only we have to take a one direction, which is you have to assume along the length direction known as axial direction, that means x direction. So this is a one dimensional flow. Very important. Very important. So this is your large parallel plate, that means the flow is one dimension. Okay, clear. Now fully developed. What is mean by the fully developed? What is mean by the fully developed? What is mean by the fully developed? That means fluid will understand. Yes, throughout the cross section, all the points there must have a viscosity. That means the fluid, see, when there is an enclosed thing is there and fluid passed within the enclosed surface, there must be an entrance region and a fully developed region. In an entrance region, the velocity may be vary, velocity will vary. But after it will develop the fully developed, that is hydrodynamically fully developed. That means there is no further velocity will increase. That means fully developed have a two meaning. What is the meaning in that? The first meaning is that if the fluid is fully developed and if you take any cross section, on that cross section, all the point along that cross section, all the points have the viscosity. Number 4, fluid behave as a viscous fluid. Number first. Number second, fully developed, that means during the fully developed fluid flow, there is no further increment in the velocity along the motion of the fluid. Clear? So this is meaning steady state, that means the parameter which is related to the fluid are inherent with the time. It is time independent. Number third, incompressible, that means density throughout the either with respect to time or location, it is constant. Laminar flow, that means fluid is flowing in the lamina, not turbulent. Okay. Viscous, that means there must be viscosity. Okay. Horizontal plate, the bottom plate is fixed, top plate is moved with a constant velocity. That means this is the flow we have at a court flow. My dear, many students get confused, sir, what is the unique characteristic in the court flow? See, my dear, in the fluid mechanics, only there are three mechanisms to fluid will flow. Only there is three mechanisms. What is the first mechanism? The fluid will flow due to the displacement of a boundary. Number first. Number second, fluid will be flow due to the difference of pressure. Number third, the fluid is flow due to the gravity effect, that is called open channel. So in all the areas of a domain of a fluid mechanics, only three things have to be a responsible fellow which is try to develop the motion of the fluid. So in this case, the fluid will flow due to the displacement of a boundary. How? One plate is fixed, other plate is moving. That means you have to displace the boundary of the fluid. So while the displacement of a boundary of the fluid, the shear stress is constant when there is no any pressure gradient. Why? Because let's see, there is a dining table on which, let's suppose there is a water is there. On the dining table, let's suppose there is a water is there. Now you have to take a cotton and put the cotton on the water which is spread on the dining table. Now you have to drag the cotton. Horizontally you have to drag the cotton. If you drag the cotton, the layer is very minimum and the modal act as a court flow. Modal act as a court flow, number first. Number second, in the rainy season, on the road, there is a layer of the water. Now you have to apply the brake of the vehicle. The tire of the vehicle is try to skid. So during that skidding, they also model at a court flow. Why? Because road is rest. Above that there is a fluid and the tire is skidding. So that is also model at a court flow. So what is the meaning of this one? In the court flow, there must be a minimum gap between the two surface which is in which the fluid is present. And one surface must be a flow, other surface must be at rest. That is the unique characteristic of the court flow. In the court flow, the shear stress may be vary or shear stress may be fixed. The shear stress is fixed when there is no any pressure gradient. So in this case, there is a minimum gap, there is no any pressure gradient. That means throughout the cross section, shear stress will fix. Why? Because we know that the shear stress is equal to mu du over dy. And du is a fix, that means lower velocity minus upper velocity, that is fixed. Why? Because this is a constant. Divided by dy is what? The gap between that plate. These two quantities is fixed. Mu is fixed. Why? Because it is a property of the fluid. Mu is fixed. So the stress is throughout the cross section is a fixed. That means stress, if you draw within the plate, there is a rectangular kind of that. But the velocity will vary. Where the velocity is maximum? Over the plate. So one velocity at the plate at that point is 0 and other velocity of the fluid is due to the movement of the plate. So the at the top plate, the velocity of the fluid is maximum, and at the bottom plate, the velocity of the fluid is 0. Both are due to the no slip condition. Both are due to the no slip condition. What is the mean by the no slip condition? That means velocity along the flow of the motion of the fluid is 0. That means the fluid particle, the tangential velocity at that point relative to the surface is 0. So plate is rest, velocity of the fluid particle is rest. Plate is moving, so velocity of the fluid particle is not by itself, it is due to the plate. So due to the no slip condition. So here it is not meaning the no slip condition, it is not meaning, sir, not no slip condition, the velocity of the fluid particle is 0. No. Velocity of the fluid particle with respect to the plate is 0. At that point in a tangential direction. That means velocity of a fluid particle with respect to the surface at that point along the tangential direction or along the motion direction is 0. That is called no slip condition. That is called no slip condition. So my dear, this is the question. It is a model in a fluid dynamic, and the model is caught flow. Caught flow. And what is the unique of the caught flow? Between the gap, the two plate between the gap is minimum. That is called caught flow. Now my dear, see, this is the 5 mm, very less distance. There is no, see, this is also, it is given. There is no pressure gradient in the direction of the flow. That means there is no any pressure variation. That means fluid must be flow within the plate only due to the displacement of a boundary. Why? Because it is in horizontal plate. It is not inclined plate. So for the horizontal plate, there is no any weight component or G component. So fluid is not flow due to the gravity. Number first. And second one, there is no any pressure gradient. That means fluid is not flowing due to the pressure. But the fluid is flowing. See, the fluid constant velocity, that means plate move, that means fluid is flowing. So fluid is flowing due to the displacement of a boundary. That is called caught flow. That means, my dear, responsible factor of fluid motion. Number first, displacement of boundary. Number second, due to pressure difference. Number third, due to gravity effect. Or combination of all these three. Okay, so displacement of a boundary beta, displacement of a boundary or between the plate and plus the pressure. That means if this is your plate is there, okay, this is your plate is there, and this plate, lower plate, is fixed. Now you have to move this plate at a velocity, let's suppose u. Okay, the gap is very minimum. Let's suppose this is your gap of the plate, which is h. Now if the plate is moving, if you take any cross section if you take any cross section beta, so the fluid which is stick to the plate have the same motion of the plate, and fluid of this lower plate have the same motion of the lower plate, but the motion is zero. So this is your velocity gradient, and this is your linear velocity gradient. If there is no any pressure, mind it, if there is no any pressure gradient, okay. Now what is the shear stress distribution? If you take any cross section, at this point, the shear stress are the same, in the same direction of the shear stress. The shear stress of all the points are same. So this is the distribution of shear stress. This is the distribution of shear stress at, so tau is constant here, shear stress is fixed, and the fluid is flowing due to the only displacement of boundary. Here the pressure gradient, yani dou P divided by dou X, if you take this is your X direction, is equal to 0. There is no any pressure variation in the X direction. So if there is no any pressure variation and the plate are in a horizontal manner, so fluid is flowing, flow of fluid only due to displacement of a boundary. Displacement of a boundary of a within the minimum gap, that is called cot flow. That is called cot flow. Okay. So this is your velocity profile. This is your velocity profile, and this is your linear, and this is your shear stress distribution. Now, my dear, so what is the fully developed flow? That means, what is the mean by the fully developed? No velocity will vary along the flow direction. Number second, what assumption is there? Steady. That means the parameter, kinematic parameter or the property of the fluid doesn't change with respect to time. Number third, incompressible. That means the density of the fluid doesn't change, and flow between two parallel plate. Now, my dear, in this direction the fluid is flowing, in this direction the fluid is flowing, in this direction the fluid is flowing. So perpendicular to the board direction, the velocity is 0. Why? Because the width of the plate is very large as compared to the length of the plate. Okay, number first. Number second, there is no any penetration in the plate, so there is no any vertical direction of the velocity. That means this is must be a one-dimensional flow. Clear? So these are very standard assumptions, so that the problem is very easy. Now, my dear, we know that what is given? Density, it is given. How much density? 800 kg per meter cube. It is given. The gap H, it is given 5 mm. Okay. Kinematic viscosity, it is given beta 1.25 cross 10 to the power minus 4 meter square per second. Okay. This velocity, it is given 4 meter per second, and this is constant. So, my dear, according to the Newton's law of motion, Newton's law of the viscosity, tau is equal to mu dou u over dou y. Okay. Now, so mu and this u is the difference between the lower and the lower difference, upper higher velocity is u minus lower velocity, At this point, what is the h height h minus at this point, what is the value of 0? 0. So my dear, this is mu u by h. Now my dear, if there is no any pressure gradients, this is constant. This is h is also constant and this mu is also constant. So this stress is constant value. So that the stresses at each and every cross section, matlab at a particular cross section from top to bottom, the shear stresses is 0. And what is the indirectly form of the shear stress? The shear stress, it is a nothing, it is a momentum flux. What is called? Momentum flux. So that means the flux of the momentum is constant at any cross section, at any cross section from top to bottom or bottom to top. That means what is the shear stress act at the plate, fixed plate, is the same shear stress will act at the top plate. Clear? Clear? Now, so put all this value, convert this mu into this one. So my dear, tau is equal to mu u by h. Now you know that, and this is constant, yes or not? This is constant. Okay, so mu you know that rho into nu into u divided by h. Why? Because we know that dynamic viscosity is your kinematic viscosity by density. Okay, so 800 into 1.25 cross 10 to the power minus 4 into 4 divided by the gap is 5 cross 10 to the power minus 3. This is your 80 Newton per meter square. And Newton per meter square also known as Pascal. Okay? Clear? This is clear, very simple. Now, we have to go to the next problem. Okay. Yes. See this one? This is also a very good question. What is that, beta? What is that? First, in the fluid mechanics, beta, you kept in two things very clearly. Very clearly. Number first categories. Who is the responsible fellow to move the fluid? Number first. Number second, how many the conservation equations? So first we talk about the conservation equation. Throughout the fluid mechanics, there are 3 conservation equations. Number first is conservation of mass. Number second, conservation of momentum. Number third, conservation of energy. Conservation of mass gives the continuity equation. Conservation of momentum gives 2 equations. First is Euler's equation. Second is Navier-Stokes equation. Third is conservation of energy, and that conservation of energy gives the Bernoulli equations. That is clear. Now, we have to go to the next. Which factor is responsible to move the fluid? First is due to the displacement of a boundary. Second is due to the pressure difference. Third one is due to the gravity. Okay. So, all the questions in the fluid mechanics, you just think which conservation of equation will applied. So, my dear, this is your tank. Very simple fundamental is there. It is not anything rocket science. Very simple fundamental. There is a tank, it is given. In the tank, there is a hole is there on the periphery. Why? Because you have to put a tap. So there is a hole, and that hole act as an orifice. Okay, no problem. The cross section area is 80. This is your 80 top cross section area. It is given at the top 80, and the cross section area of this outcome is given AO. Here clearly mentioned this is your reference datum line at y is equal to 0. That means it must be y, it is in this direction. So at y equal to 0 there is orifice, and at y equal to h there is a free surface. There is a free surface. Now what they are asking, water flow out from a large tank. What is mean by the large tank? We have to discuss. Of a cross section area AT is equal to 1 meter square throughout a small rounded, that means orifice. So it is not like the someone says you ki orifice, it is in which shape. Generally students say that sir orifice it is circular. No, it may be rectangle, it may be elliptical. Orifice it at any geometry, but in generally the orifice in a round hole, rounded shape, that means a circle is there. Okay, cross section area, it is given the cross section area orifice 1 centimeter square. See the beauty. The area is, that means this area is 1 meter square, this area is 1 centimeter square. So this area is very minimum as compared to the top area of the tank. This have a meaning. That means A of orifice is very less than A of the tank. This have a meaning. I will discuss you. Locate at y equal to 0. That means orifice locate at y equal to 0. That means you have to place a datum at the orifice. Okay. Initially the water level. That means initially. Why they are given initially? Why? Because water is flowing. So initially that means at a time t equal to 0. Initially that means at a time t equal to 0. At a time t equal to 0, the water level is h. That means just start to measure, the water level is h. What is that? H is the water level. Now, and the water level is 1 meter. Okay, the water level is 1 meter. The acceleration due to gravity, it is given, no problem. Neglect the any losses. We have to discuss what is the losses. Any losses, nothing there is a losses is there. Okay, the time taken by the water in the tank to reach the level y equal to h by 4. That means what's the time will take? What's the time will take when y equal to h by 4, and we have to take measurement at this point. So initially this is h height is there. H height is there. At, let's suppose at time t equal to 0. Let's suppose at time t equal to 0. Now you have to measure the level of the tank in the water, level of the tank, level of the water in the tank when h is equal to h by 4, at what time they reach. Good evening beta. So at what time they will reach? So my dear, which equation you have to apply? First tell me which equation is applied. First equation only conservation of momentum. First is conservation of momentum. Okay. Yes, it is right. No, conservation of mass. What is the conservation of mass? Conservation of mass, that means mass in, mass exit is equal to rate of the change of a mass of a control volume. So this is your control volume. This is your control volume. So first you think which equation you have to apply. The equation apply, it is your conservation of mass. Okay. What is the conservation of mass? What do we know that conservation of mass? Conservation of mass. What is the conservation of mass? Mass at inlet, mass flow rate at inlet, okay, minus mass flow rate at exit, okay, is equal to rate of change of a mass with this in the control volume. Okay. So why? Because this is the unsteadiness. Why? Because this is your unsteadiness. Why? Because the rate we have to take, the property of the control volume, that means mass of the property of the control volume, that will change with respect to time. So this is 0. This is not 0. So this is the unsteady problem. Okay. But if there is a tank is there, so in the tank only exit is there. There is orifice is there, so only exit is there. There is no any inlet. That means you have no any chance to put the water into this one. No inlet is there, so only exit is there. So inlet it is 0. What is that? The inlet it is 0. Inlet it is 0. Mass flow rate at inlet it is 0. Okay. Now exit is there, and exit from orifice. This is from orifice. From orifice. Okay. So it is there. It is not 0. It is not 0. 0. So this is conservation of momentum. You have to write COM is a conservation of momentum. This is conservation of mass. Conservation of mass. Okay. Conservation of mass. What is the conservation of mass is there? Okay. So first we have to find the mass. So this mass is the control volume, and this mass is the exit from the orifice. Exit from the orifice. So there is a two mass. Mass is the exit from the orifice, and this is the mass of a control volume. So what is the mass of a control volume? You have to take a time t equal to at this initial time. So what is the mass? What is the mass? Density into volume. You know this one. And what is the volume? Area into velocity. Yes or not? Now, if, my dear, if this is your tank, very important. If this is your tank, okay, and this is your height h. This is your height h. Clear? So what is the velocity at here? Please tell me, what is the velocity at here? Exit velocity. This velocity is root under 2gh. Why? Because we have no any considering any loss. So the velocity at exit from the nozzle is root 2gh, kinetic energy. Okay. So the potential energy converted into the kinetic energy. So this is the velocity. So what is the velocity? Rho area into velocity root 2gh. That's it. Okay. Now my dear, you have to apply this equation. So what is the mass minus exit mass flow rate is equal to mass of the control volume divided by dt. Yes or not? Yes or not? So put the mass at exit. So what is the mass at exit, beta? So exit mass is have an exit velocity. So what is the mass? Mass have an area into velocity. What is the mass have density? Density is fixed. What is the density here? Same density is here. So density is fixed. Area, if you take this point exit velocity, so this is your exit condition. So where is the exit condition? This is your exit condition. This is your exit condition. So at exit condition, what is the mass? What is the mass? Rho A at the exit. And what is the area of the exit? Area of the orifice into root 2gh. Clear? So this is your minus rho area of the orifice root 2gh. Clear, beta? Is equal to. Now, my dear, this is the mass of a control volume. So this is your control volume. This is your control volume. So what is the mass of a control volume? Mass of a control volume, that means d by dt. What is the mass of control volume? Area. Area. What is the area of this control volume? A top. Area. A top. Area into height. What is the height? H. And what is the velocity? We don't know. We don't know mass. So we have a area. Area A rho into this density. Okay, na? So this volume you can write like that. This is the mass flow rate. So this is your mass flow rate. If you write velocity, so this is equation in kg per second. Kg per second. So this is your mass flow rate. Clear now? This is your mass flow rate. Now we have to find the mass of a control volume. So this is a mass of a control volume. So mass of a control volume. So what is the mass of a control volume? Mass of a control volume is your mass of a control volume. What is the mass of a control volume, beta? Rho area AT into rho A into rho A volume. Find the mass of a control volume. What is that? Density into the velocity volume. This is not mass flow rate. So you don't consider with the rate basis. So if you rate basis, this is a volume flow rate. What is the volume flow rate? Area into velocity. Area into velocity. And what is the mass? This is a mass. So rho, what is the volume of this one? Area into height, this height h. This height h. So this is the mass of a control volume. This is the mass flow rate through this orifice. Clear na? So what is the A into h? Density you have also there into density. Clear? So you have to solve this equation. So if you separate this dt, so dt is equal to A top by AO into 1 by root 2g dh by root h. Clear? Now you have to integrate this time. So t is equal to integration dt and start with the time 0 to t. So you can integrate. This is constant, this is constant. So at by ao is constant into 1 upon root 2g. You have to integrate from this height. At a time 0, what is the height of this level? H. At a time t, how much that h? H by 4 is equal to dh by root h. Now you have to integrate this one. After the integration, this is time, it is given minus at by ao into 1 upon root 2g into 2 into root under, this is the final. You have to take final. Let's suppose this is a final, h final, and this is your h initial. So this is your root under h final minus root under h initial. And you have h final, h initial. So these are the relation. Put all this value. So the time it is in second 2258.8 second. Clear? So my dear, today we have a very less time. So we will end up here. Okay. And after that, tomorrow session, we'll cover again this same year problem, little bit there, 2 and 3 problem for the turbo machinery. In the turbo machinery, so we have to discuss tomorrow turbo machinery and along with the 2020 question. Okay. So up to that, stay tuned. Bye bye.